Hi students, welcome to Science Extension and Module 3, the Data, Evidence and Decisions. This is video number 12, and we're going to start this whole idea of statistical analysis of data sets with a particular focus on inferential statistics. So what you need to be able to do is to apply appropriate performance measures to the statistical analysis of a data set relevant to the scientific research project. So now we're going to think about what it is that you need for your data and have a look at the whole range of different things that we might be able to look at, the range of tools that might be available for you as you are carrying out your own statistical analyses. So the first thing we need to do is we need to think about statistical analyses in general. And the most challenging thing is that there are so many tests, and there are a few that are listed that we need to be aware of, but if you study statistics, you'll go through a much broader range of tests than the ones that we cover in this course. Because there's so many, we need to kind of trim it down a little bit and focus in on the ones that are going to be most useful to us. What we need is a quick way of determining which tests we need to use in a particular situation. Which test is going to give us some important information and help us to determine whether or not to accept or reject our null hypothesis. And we'll talk about that in this video too. Scientific data can be classified in many ways, but for our purposes in science, it usually comes in one of two different types. That is, data which may be correlated, there may be a predictor and an outcome, and data which may be causal. That is, there's a direct relationship between the independent variable and the dependent variable, such as when you make a specific change to the independent variable, it causes a consequent change to the dependent variable. Earlier in this module, we talked about the fact that data could be descriptive, categorical, like color, continuous, numerical within a range, such as human heights, or discrete, whole numbers, such as atomic numbers. So we don't have a 1.5. We have an atomic number of 1, which would be hydrogen. We have an atomic number of 2, which would be helium, but there's nothing between 1 and 2. So that's that idea of discrete. Variability in the data is critical to our understanding and interpretation of statistics. Bruce wrote this: "At the heart of statistics lies variability. Measuring it, reducing it, distinguishing random from real variability, identifying the various sources of real variability, and making decisions in the presence of it." That's what we're focusing on here. Variability, change. And is there any relationship between the changes that we are making in our experiment and the measurements that we're seeing as a consequence of those changes? It's always about the aim or the hypothesis in science. So we've talked about hypotheses as being educated guesses. We set an aim to do something, and then we state a hypothesis, which usually is stated in terms of a general relationship between the two variables that we're interested in. We gather and analyze our results so that we can say that our hypothesis has been supported, we can accept that hypothesis, or that the data doesn't support our hypothesis, and maybe we might reject that hypothesis based on that Popperian idea of falsification. And a falsifying hypothesis can be falsified if we discover a reproducible effect which refutes the theory. That is, if we find evidence that suggests that our hypothesis might be wrong. The idea of a relationship between two variables is not being supported by the data that we have. But how do we know? How do we know to what degree? And most of the time, the experiments that we've done up to this point, we've probably gone, yeah, our results kind of support our ideas, but we want to be a little bit more deliberate than that. We want to make sure that our statistical testing specifically helps us, under certain conditions, determine the degree of confidence that we can have in that our conclusions will allow us to accept or reject our hypotheses, that there's a clear relationship between the evidence that we've determined from the data we've collected that allows us to make conclusions in relation to those hypotheses. There's a nice little flow chart provided by the New South Wales Department of Education, which gives you a good quick overview of how we use statistics as part of our evaluation of the hypothesis. And what we're going to look at now are two very clearly distinct types of hypotheses. So the first of these is called the null hypothesis, which means no relationship, basically no difference. We are seeing or we're suggesting that there is no difference between two variables. That is, if you change one, it has no effect on the other. The alternate hypothesis, which is the second hypothesis that we could write, is the alternate. So if the null is there's no relationship, the alternate is there is a relationship. And usually we'll talk about the direction of that relationship. Now, we may not always, but usually we will have something to say about the direction of that relationship. In order to test, it's much easier to test our null hypothesis. There's no relationship. We're going to talk about some different statistical tests we can carry out. And we're also going to talk about our confidence levels, our alpha levels. And that is, generally speaking, going to be around about the 0.05, so the 5% mark, which is basically saying that there's a 5% chance that we have obtained this particular set of results that support this particular idea that we have. So you can see that the lower that percentage gets, the less likely that is to have actually been the case. So we have to have a cutoff, and the 5% is usually the percentage that is chosen. Perhaps if you're looking at doing medical research, you might go smaller than that, but that's the generally accepted value. So our statistical tests are always going to begin with a scientific hypothesis. We need to make sure that we have them, generally two, the null hypothesis and an alternate. And if something's going to be scientifically valid, then it does need to be falsifiable. So we need to remember that idea of Popper about falsification. And partly what we're trying to do is to see if we can test our null hypothesis and ideally falsify it. And if we can, then that means we can reject that null hypothesis, which then tells us if we reject the no difference hypothesis, then we're accepting that there is a difference, which is partly what we're trying to do. But we also have, in order to do this, to apply different statistical tests to the data set that we have so that we're able to determine a value which helps us to determine whether or not we will reject or accept the hypothesis. You'll find lots of information about the null hypothesis and the alternate hypothesis. Important things to be aware of are firstly the symbols for each. So H0 or H subscript 0 is the null hypothesis, 0 being zero relationship between them, and the alternate is H1, and there is a relationship between them. Null is no value, so a null result is a nothing result. So null hypothesis, no relationship between the variables that you're interested in. Alternate hypothesis, there is a relationship. And the most important thing to remember about the alternate hypothesis is that we are going to try as much as possible to indicate the direction. So rather than just saying null hypothesis, no relationship, alternate hypothesis, there is a relationship. What we'll do with our alternate hypothesis is usually try and look at the fact that maybe the mean of group A is bigger than the mean of group B. So that might be a specific difference that we're after. So what are we going to do? Well, according to Hinton, the power of a statistical test can be defined as the follows. The probability that when there is a genuine effect to be found, the test will find it. That is, it'll correctly reject a false null hypothesis. So we just want to make sure that we're clear about that type 1 error, that we don't want to convict someone who's innocent. That is, if there is no relationship, we don't want to find a relationship. We want to make sure that if there is a relationship, that we do actually find that. If there is a false null hypothesis, if there is a relationship, that our statistical test will actually find that. The Hinton book, Statistics Explained, is a very, very good book. It's a very complex book, covers lots and lots of different types of statistics and well beyond what you need for this particular course. But there's some interesting things that you can pull out of that if you want to have a look at it. So when we look at our data, there's several questions that we can ask. Do two samples of data represent a single population with a similar mean? And if they do, then we're looking at t-tests, and there are a couple of different types of those. Is it categorical data that's drawn from a particular distribution? And therefore, we will talk about what we might expect to get in a population and what we observe from the data that we've collected. And that would involve a chi-squared test. And what about if two samples of data have come from the same population, but we're not sure whether or not they have equal variance? Well, then we can use the F-test. So there's a couple of different tests that we're going to look at, and we'll look at each of these in a bit more detail in separate videos. Irrespective of which of the tests you decide to go with, though, you are going to have to calculate a test statistic. Fortunately, applications like Excel do a lot of this stuff automatically, and so as long as you know which test to apply, you can throw the data into Excel, and you can then use the tools in Excel, which we've already looked at in some of the other videos and which we will look at further, to do all the number crunching for yourself. So a normal distribution with unknown population standard deviation might give you a t-test, n-1 degrees of freedom. A normal distribution with a known population standard deviation could be a z. Distribution to determine whether two samples have equal variance could be an f. And in each of these situations, you can see we've got some symbols that are standard. So an X with a bar across it is our mean or our average. S is the standard deviation of a random sample of usually a size of n, little n for a sample, and big N usually for the whole population. The normal distribution is the wider population, and that has a mean of mu and a standard deviation of sigma. So these are the general differences. Sometimes we're looking at a population, sometimes we're looking at a sample from that population or several samples from that population and comparing them with one another. One of the things that we'll talk about is degrees of freedom. Now, degrees of freedom is an important concept when we start to look at our statistical analyses, and when we calculate our test statistic, we need to use information from the data in our calculation. So that could include the total number of scores, the mean of all of those scores, the standard deviation, the range, the maximum, minimum, all of those sorts of things. And we need to make sure that we know the number of scores that are free to vary in the analysis. Now, in practice, this is the total number of scores less 1. So if I tell you that the class average is 75%, and there are 10 students in the class, and I give you 9 of the marks in any order, you can calculate the 10th. If you know the mean and you know 9 of the scores, you can calculate the 10th score. You don't have to know that one, just a bit of simple maths will give it to you. And that's what we mean by degrees of freedom. 9 of those can change, but when you lock 9 of them in, the 10th one then becomes locked in automatically. So that's what we're talking about in this idea of degrees of freedom. In large samples, dividing by n or n-1 don't tend to have a lot of change. So if you're dividing something by 100 as opposed to 99, not a lot of difference. If you're dividing a number by 2 as opposed to 1, big difference. So very small sample sizes are where we find bigger effects of this idea of degrees of freedom. So that's one of the important reasons why you need to make sure that your samples are as large as you can make them. We're also going to talk about the p-value or the probability value, and this p-value evaluates the degree to which the sample data supports the null hypothesis. So we're going to get a value and we're going to see to what extent this can be used in the determination of whether we're going to accept or reject our null hypothesis. The p-value may be regarded as the probability, hence the p, of obtaining a set of data by chance if the hypothesis is true. So that is, if our null hypothesis is true, no relationship between our variables, what is the chance that we just obtain a data set that shows us that? And obviously, if that is the case, there's a fairly good chance that we'll find that. If it's not the case, it's going to be a lot more difficult to find. What we need to do is we need to compare our p-value with the value that we have set, our alpha value. That is, again, linking back to our type 1 error, that statistic that tells us we think in order not to condemn an innocent person, we want to make sure that we're not going to reject a hypothesis when there is no relationship, that we want to make sure that we've set that value fairly low. So we want to make sure that the p-value is lower than whatever it is that we've set the alpha value as. And as we've talked about before, generally speaking, this alpha value is going to be set at 0.05 or 5% value. So we're looking at a probability lower than that in order for us to reject our null hypothesis. So what is the alpha? The alpha is our significance level. So this is the value that we've chosen to set as our value of significance. So if it falls into that little region beyond that significant level, then we're going to say the chances of this happening by chance, very, very small. So we're actually going to reject our null hypothesis if our probability falls below the significance level. So that is if our p-value is less than 0.05, if that's what we've set as our alpha level. This is where it's very important that we make sure that we've got clarity around the null hypothesis, the alternate hypothesis, the statistical test that we're going to carry out, the test statistic that we calculate based on our data, the p-value that's associated with that test statistic. Now, there are books and tables that you can look up those for the different tests, but most of the time, if you're using a statistical application, SPSS, or even the tools that are available in Excel, then you can get straight to a p-value, and then you can compare that p-value with your alpha value, your significance level, and that's going to tell you whether or not to accept or reject your null hypothesis. But of course, the question is, which of those tests do we actually use? Which statistical test do we choose? How do we use those tests to test different types of data? And then how do we make conclusions based on that? And to do that, we're going to have to look at each of those tests separately, and we'll do that in subsequent videos. Thanks for watching.